Swayam Prabha. Digital India. Educated India.
In the last class, we saw some introduction to matrix algebra or linear algebra. We saw how to add two matrices, how to multiply two matrices, and then we moved on to indicial notations, wherein we saw what a dummy index is, what a free index is, and then we moved on to vector algebra, wherein we saw some basic vector operations like vector addition, scalar multiplication, and then dot product, cross product, and scalar tuple products, and we understood the geometrical meaning. In particular, we understood that vector is a direct line segment for us, it is a geometrical object rather than a set of numbers. Now, in this class we will see how we can transform a geometrical object into a set of numbers, so that we can do algebra with it. You need this because in today's world we are using computers or calculators to do the calculations, which can work on only numbers, but cannot work on geometrical objects. So, we need to convert a geometrical object into some format where we can do algebra with it, that is into some representation which has numbers, using which you can do some calculations. It is similar to representing numbers using a basis 1 to 0 to 9, or representing numbers using only 0 and 1, which is a binary format which the computer uses. So, there is an equivalence between these two representation of number system, right. Similarly, we will see today how you can represent a geometrical object of a vector using some numbers. Okay. So, basically in the last class we saw that this data line segment is what we call as a vector. Let us denote it by a with underscore. Okay. Now, let us say that I am defining three other data line segments called E1, which you would have denoted by I vector, or which you can denote equivalently by an Ex. These are different symbols that are used to represent this data line segment, and another data line segment E2, which we will call it as, which you might be using the symbol J in your previous courses, or you can denote it by Ey, which we will use. E2 and Ey are notation that we will use frequently in this course. Another third data line segment which is E3, which will denote it by K or Ez. Okay. Now, this data line segment A you want to represent using this E1, E2, E3 as the three data line segments. You want to use those three data line segments and represent A. What does this mean? It is like representing numbers, say 99 as 9 into 10 plus 9, there is a representation of 99, right. Similarly, you want to represent this A using these three data line segments E1, E2, E3. Okay. So, when you write A as A1 E1 plus A2 E2 plus A3 E3, or succinctly this can be written as AI EI. This is the reason why I am using 1, 2, 3 as the index for the basis vectors rather than x, y, z or I, j, k for the basis vectors. Okay. As we said in the last class, I is repeated twice and hence it is called as a dummy index, and hence it has to be sum from 1 to 3, which is what I will want to stress from now on. Okay. Now, how do I find this AI? I can find AI by projecting A onto the basis vectors Ei. Tilde or underscore for me means the same thing. I am not distinguishing tilde from underscore. Sometimes I use tilde, sometimes I use underscore. Okay. So, this Ei is a basis vector. So, Ai is the projection of A onto Ei, that is the meaning of Ai, the component of the vector Ai. Okay. Now, let us combining these two, I can write A as A dotted with EI times EI. Okay. This is a general representation of a vector using 3 other data line segments. So, any vector you can represent using 3 data line segments. Why do you need 3 data line segments? Because your space is 3 dimensional. If your space were to be 2 dimensional, then you will require only 2 basis vectors, which might be x and y or Ex Ey or E1 E2 and so on. Okay. So, you are represented a vector as this. Now, how do I know that Ai is A dotted with Ei? That comes from the definition of the dot product, that you are interested in projecting A along the Eith direction. Okay. So, that is how you know that it is a projection. Ai is nothing but A dotted with Ei. Now, this 3 data line segment that I chose E1, E2, E3 was arbitrary, right. I came and drew some 3 data line segments and chose it to represent any other data line segment which was A. Okay. Now, say your friend comes about and says that he does not want to use this data line segments, but he wants to use something different. He wants to use this, which we call it as E1 star, E2 star, and say E3 star, he agrees with your direction, and this is E3 star. That is, he has rotated the basis vector by an angle theta in the anticlockwise direction to get E1 star, E2 star and E3 star about the z axis. Okay. So, basically now he wants to represent this vector A using the same vector A using the basis vectors E1 star, E2 star, E3 star. Then what will A be? A in this red basis would be A1 star, E1 star plus A2 star, E2 star plus A3 star, E3 star, or in short form Ai star, Ei star. Okay. Or I can write this A as A dotted with Ei star, Ei star. Okay. Same thing, where Ai star is A dot, similar to this I will have Ai star to be given by A dotted with Ei star. Okay. So, I have these 2 different representations. So, there is no sanctity that the number A1, A2, A3 alone represent this vector, that is what we are trying to understand here. The numbers, if I write A as A1, A2, A3, this column vector alone does not represent A, but even this column vector A1 star, A2 star, A3 star represents the same vector A. Okay. So, there is not that only one set of numbers 1, 2, 3 represent a vector, there will be n number of other 3 combinations will represent the same vector. What are those 3 combinations? Given a combination is what we are trying to find out now. Okay. So, what is the relationship between, what is the relationship between Ai and Ai star is the question we are trying to answer now. Okay. They represent the same vector A, right. Okay. Both Ai and Ai star represent the same vector A. So, the magnitude of A has to be the same and its direction, relative direction with respect to any other data line segment has to be the same. So, what does this mean? I go and substitute for from this equation, I take this equation, A is A dotted with Ei, I rewrite this as A dotted with Ej star, J is repeating twice. So, I can replace J with K or I or A or B or C or D, it does not matter, since it is repeated twice I can change the symbol that I use to represent them, that is what I have done. Now, for A I substitute the fact that it can be written as this is A, I use this and substitute for A here to get A as AI EI dotted with EJ star times EJ star. Okay. Now, then I go back to this equation where I want to find AJ star would be A dotted with EJ star, which will be AI, or let me say this is B, that will be AI EI dotted with EJ star dotted with EB star. Okay. I could not have used J here because that violates the summation convention. J will appear thrice on the same side or equal to sign, which is not allowed. Okay. So, this is this. Now, what do I know? I know that EI dotted with EJ will be canonical delta, delta Ij, right. From what we defined the canonical delta in the previous class, it will be 0 if I is not equal to j and 1 if I equal to j. What does this mean? The bases are orthonormal bases, that is the magnitude of each of these basis vector is 1 and they are mutually orthogonal. Okay. E1 dot E2 is 0, E2 dot E3 is 0, E3 dot E1 is 0. Okay. So, they are mutually orthogonal and the magnitude of each of these vectors is 1, that is what this orthonormal basis mean here. Okay. Similarly, I have EI star dotted with EJ star is delta Ij. Okay. So, from that I get that this is AI delta JB for this become delta JB, and this I write it as QIJ. Okay. It is easy to see that EI dot with EJ star is not delta Ij because they are not orthogonal. Okay. So, let us write now for the transformation that we had. Let me redraw the figure, the axis E1, E2, E3, and I add the axis rotated by E1 star, E2 star and E3 star are like this, that is anticlockwise rotation of theta. So, now what is E1 star in terms of E1 E2? I have to project E1 star onto E1, that will be cos theta E1 plus projecting this onto this is 90 minus theta. So, projecting this onto this, it will be sin theta E2. Again E1 star, E2 star, E3 star are of length unity and hence you can write this as this. Similarly, E2 star would be minus sin theta E1 plus cos theta E2 and E3 star will be same as E3. Okay. Now, let us find this matrix Qij, which was EI dotted with EJ star. Going back to the equation, you can see that Qij is EI dot EJ star, right. So, you want to write what this matrix Qij is. Okay. So, it will be E1 dotted with E1 star, E1 dotted with E2 star, E1 dotted with E3 star. Here it is going to be E2 dotted with E1 star, E2 dotted with E2 star, E2 dotted with E3 star, E3 dotted with E1 star, E3 dotted with E2 star, E3 dotted with E3 star, and for this E1, E2, E3 star, what you get is you get it as cos theta minus sin theta 0 sin theta cos theta 0 0 0 1. Okay, that is what you get the Qij matrix to be. So, now going back to our previous equation, AB star is given by this expression. Now, I can simplify this expression further. If J and B are not same, they are going to be 0, right. So, I can replace J with B or B with J. So, let me replace J with B. So, this will be AI Q I B, okay, Q I B. Now, you can see that there is a problem here. If I define it like this, what I have to do is, let me come to the next page. What I add, the final equation I had was this AB star equal to AI QIB, right. I add AB star is AI QIB. Okay. What does this mean? I have to sum this index I, and B is a I is a dummy index and B is a free index. So, this means I have A1 Q1 1 plus A2 Q21 plus A3 Q31 A1 Q12 plus A2 Q22 plus A3 Q32 A1 Q13 plus A2 Q23 plus A3 Q33. This is the meaning of this equation, right. Now, this is not equivalent to multiplying this vector Q with this A. This means this is not equal to this, but this means this is equal to A transpose multiplied by Q. If I think of A as, if I think of A vector as being A1, A2, A3, this is the operation that gives me this initial notation, but I want to write like this. Okay. So, what do? I can write this as, now AB star can be written as Q transpose IB into AI. Okay. So, in other words, A star is the Q transpose A, where Q is this matrix. Okay. So, you can see if I transpose this, I will get the right addition of the terms here. Okay. Okay. So, this is the representation, final representation that we got for A star. Okay. Now, let us see what happens for the case that we have considered. Okay. So, A star would be cos theta minus sin theta cos theta 0 0 0 0 1 into A1 A2 A3. So, this will be cos theta into A1 plus sin theta into A2 minus sin theta A1 plus cos theta A2 and A3. Okay. This is A1 star, A2 star, A3 star. So, for a planar rotation, theta can be any value. So, all this set of values that you get by multiplying cos theta and sin theta with A1 and A2 are admissible components of the vector. All this what you get A1 star, A2 star, A3 star are also admissible components of that vector A and represent the same vector. Okay. Now, let us find, is there any restriction on, is there any restriction on the matrix Q. Okay. Let us answer this question. So, basically now we add that A star is Q transpose A, right. This is the equation we got in matrix multiplication term. This is what it is. In component terms, you add A star B as Q I B A I, okay. Q I B A I, okay. So, basically now what do we know? If A star also represents the same vector A, if A star also represents the same vector A, if A star also represents the same vector A, then the magnitude of this vector has to be the same. If A star also represents A, the magnitude of A should remain same, whether I represent it using A1, A2, A3 or A1 star, A2 star, A3 star. Okay. So, I am interested in finding what the magnitude is, interested in finding the magnitude of A, that we saw in the last classes A dotted with A over a square root. So, this will be AI EI dotted with AI AJ EJ square root. I have used the representation of the vector as AI EI AJ EJ. I can be replaced with J because I and J are dummy indexes. So, this will be AI AJ delta Ij power of, again this canonical delta, if I is not equal to J, it is going to be equal to 0. So, what I can do is I can replace this I with J, which will become AI squared power of, this is AI square is I repeated twice. So, this will be nothing but A1 square plus A2 square plus A3 square power half. That is why I can cancel this 2 with this half. It is sum, it means I have to sum I from 1 to 3. Okay. Now, let us do the same thing for the primed starred coordinate system. AI star EI star dotted with AJ star EJ star power of, this also I will get it as AJ star squared power of, and I know AJ star squared is, now how do I find AJ star squared? This can be written as A star transposed with A star, right. A star, A for me vector is a column vector. So, A star transpose will give me A1 star, A2 star, A3 star, and this is A1 star, A2 star and A3 star. So, this gives me AJ square. Okay. Now, substituting this for A star, what do I get is, I get it as Q transpose A the whole transpose Q transpose A vector. So, you know that A matrix, B matrix multiplied and transposed is B transpose A transpose. Okay. So, this will become A transpose Q transpose A. Okay. So, that is AJ star squared. Okay. So, you have norm of A given by ai squared power of, that is nothing but A transpose A, this is nothing but Aj squared power of, which is nothing but from what we found here, this Aj star squared, we are using that expression in here to get it as A transpose Q transpose A is what we got. Now, from this 2 we find that I can write it as A transpose into, this has to be equal. So, equating from those 2 I will get it as identity matrix. We will see what this is in a short while. Q transpose times A has to be equal to 0. Okay. Now, this identity matrix means the diagonal terms are alone 1 0 0 0 1 0 0 0 1. So, you can see I have done nothing. If I multiply this with A, I will get back A. So, what I have done is I have written this as A transpose identity matrix times A, and essentially I have done nothing in here, just that I have introduced one more matrix here for simplification. This has to hold for any A. I require this has to hold for any A, which implies that Q transpose has to be an identity matrix. Okay. What does this mean? We know that if I have A and A inverse, then this will result in an identity matrix, right. This is called as inverse of A. Okay. That will be an identity matrix, which means here for Q inverse is equal to the transpose of Q. Okay. That is what this means. The inverse of the matrix is the transpose of the matrix. These matrices are called as orthogonal matrix. Such matrix are called as orthogonal matrix. Okay. Where the inverse is transpose. Okay. So, that is the restriction on, this is the restriction on Q. So, Q has to be an orthogonal matrix. Okay. For it to be able to map different components of the same dotted line segment. Okay. That is a restriction. Okay. So, let us go back here, let us check whether this satisfies, this Q satisfies that property. Let us check whether this Q satisfies this property, that it is an orthogonal matrix. Okay. For our example, Q is cos theta minus sin theta sin theta cos theta 0 0 0 0 1. I am interested in finding Q transpose, what will it be? So, you can see that it is going to be, if Q is that, Q transpose would be cos theta minus sin theta cos theta 0 0 0 0 1, and if I multiply this, is going to be cos square theta plus sin square theta 0 0 0, again cos square theta plus sin square theta 0 0 0 1. From trigonometry you know that this is also equal to 1, and hence it is an identity matrix. Okay. So, that is why it was a, that is how it forms a transformation matrix. Okay. Okay. So, what we have understood till now is I can represent a vector A as ai ei, where ai or ai star ei star, or a star would be related to A as q transpose A, where q I j is E I dotted with E j star. Okay.